Hi, my name is Ava Martino and I will be presenting on Lab 5 of Physics 2211. This is the Choose Your Own Adventure lab and I chose to analyze the world's largest rope swing. For reference, here is a video of the rope swing that we are trying to model. In the introduction, I will outline the purpose of the lab and introduce some key concepts used during the experiment. I will analyze the rope's motion from the video and create a computation model in GlowScript based on the data given in the video. Then, I'll analyze the results. Finally, I will address a few discussion questions. The purpose of this lab is to create a computation model based off of the largest rope swing and determine whether energy is being conserved. In this experiment, the system is the swing and the person on the swing, while everything outside of the system, such as gravity and the earth, constitutes our surroundings. For a quick preview of the result, the change in total energy will be 0. Some key concepts used include the energy principle, which is the change in energy of a system is equal to the work on the system plus the exchange of thermal energy. You can see the equations for the energy principle on the right. Delta E is equal to W, and delta E is equal to delta K plus delta UG plus delta US. Newton's second law was also utilized, which states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Additionally, we utilize the position update and velocity update formulas, which you can see on the bottom. Here's a short segment of my computation model based on the data given in the video. For the initial conditions, I changed the person's mass to be about 70 kilograms. The initial position was 45.72 in the negative x direction and 0 in the y direction, which we obtained from the video. The initial velocity was set to 0, 0, 0 because the swing came from rest. Finally, we changed the time to 0 and delta t to 1 over 60. So I first found L by subtracting the person's initial position from the original position. Then I found L hat and S. I then used the position and velocity update formulas in order to continuously find the new velocity and position. Next, I found the system's energy by using the kinetic energy formula and potential energy formulas and added them together to find the total energy of the system. I found K by using the kinetic energy formula, which is 1/2 times the mass times velocity squared. I found UG by using the formula for gravitational potential energy, which is mass times gravity times the height. Finally, I found E by adding K and UG. Here is a result of the computation model. The y graph has a nice oscillating motion to it because the swing moves up and then down repeatedly. And to the right is the final result of my code. Now, is the energy principle satisfied? Because there is no work being done by the surroundings on the system, energy is conserved. So the energy principle is satisfied, meaning there is no loss or gain of energy within the system. This can be seen with the graph on the bottom right. The orange line stays at 0 throughout the entire motion of the swing. However, in real life, other forces, such as drag, might have influenced delta E. Is the rope like a spring? At the atomic level, the rope can be modeled like a spring because of the atoms that have a spring-like bond between them. And this spring-like bond has a large stiffness K. You can see this pictured on the right.